small technical issue. But that doesn't matter now because you can see us and hopefully you can hear us. And I'd like to welcome you to all of those around the world that has chosen to log in with us this evening. Today, we are going to be looking at Earth's catastrophic past. And our guest speaker today is Dr. Birgir Oskarsson, and I'm going to invite him to present his speech with you today. Thank you.
Thank you, Natalie. Hello, everybody. It's a privilege to participate in this virtual conference on matters of faith and science. And I want to thank the organizers for the initiative in arranging this event and for inviting me. This is a new experience for me to talk to such a wide and international audience from the comfort of my home. But I believe this is the wisest thing to do nowadays with the current COVID-19 pandemic. My name is Birgir, and I'm from Iceland. I work as a geologist doing research in the field of volcanology and making geological maps of the beautiful volcanic terrains we have here. Besides this, I occasionally had the chance to do research on active volcanoes like the 2014 Holuhraun eruption, a spectacular eruption. And these photos here are from the first phase of the Eyjafjallajökull eruption in 2010 with a beautiful lava fall, very rare phenomena. Here you see another photograph of these lava falls that formed in that first phase of Eyjafjallajökull, besides a waterfall. So these are spectacular sceneries. And yes, I have an exciting job, although not the safest, but I have great fun and I'm very passionate about it. But I'm also a person of faith, a Christian, and very enthusiastic about exploring this interface between science and faith. But I recognize the subject is extremely complex, and there are various ideas circulating out there, and some may sound even strange, not put in the right context. And some are indeed very strange and not sound arguments and need to be revised. So even Christians disagree among themselves on the nature of some of these arguments. So I want to make some preliminary remarks here just to set the stage for a deeper conversation about these things. So what is the nature of Christian arguments? Now, Christians do not adhere to methodological naturalism, which is the assumption that nature is all there is. This is a key point in this conversation. Methodological naturalism was a term as part of the scientific method sometime during or shortly after the Enlightenment period around the 18th century. The motive was to free science from superstition and religion. Now, there was a problem. Methodological naturalism is a philosophical concept, which is not verified by science. It is a religious system on its own. It claims a priori that nature is self-creating and directional towards purposeful complexity. The Christian methodology endorses a more holistic, a more integrated approach that explores the best from all fields of knowledge. That is to say, it takes the best from science, from philosophy, from history, theology, etc. At least it tries to. Now, Christians think that there are many good arguments that together make a cumulative case for God's existence. Now, if you're not familiar with these arguments, I really recommend or would encourage you to learn them, because these are foundational for these discussions. We have seen some variation of these arguments here in our previous talks, but these can be framed philosophically and are easy to memorize. There are many good Christian philosophers working on these arguments. And I could mention here a few. The cosmological argument, or there are a few arguments that are cosmological, teleological arguments that involve design in the universe, biological design, ontological arguments that deal with existence, transcendental arguments deal with morality, conscience, free will, laws of logic, and many more. The great founders of modern science approached knowledge holistically, and were not bound to naturalism. I could mention here Isaac Newton, Louis Pasteur, Blaise Pascal, Johannes Kepler, and there are even some geologists in the list. Nikola Steno, which is the founder of modern stratigraphy. He kind of determined the relative position of the rocks to each other. Then there's Louis Agassiz, the father of kind of modern glaciology. There's even a man called Antonio Snyder. He was the first to suggest a theory of continental drift or plate tectonics. But he was a catastrophist and postulated that the plates had moved rapidly during Noah's flood. Now, the Christian worldview provides the foundations for science and intelligibility. Now, science presupposes natural order. In the Judeo-Christian worldview, God creates systems governed by natural laws. That is to say, a universe with galactic, planetary, geological, and biological systems. And this is very important, that God is not nature, as in pantheism. He transcends nature. And therefore, nature can be studied and explored because it follows natural laws. On naturalism, we could say pockets of order are totally accidental. If our universe is one amidst many in a multiverse, we're just a pocket of order, but it's all accidental and therefore difficult to be maintained and trusted. And science depends on natural order for predictability. Now, science presupposes intelligibility, that nature can be understood. The scientist depends on conscience, free will, laws of logic. Laws of logic would represent mental order. And these attributes cannot be taken for granted on naturalism. Chance does not have these properties. All these things would be mere illusion. Now, when it comes to natural sciences like geology and biology, many become uneasy when they hear Christians connecting their worldview to these fields. Some people prefer religion to be more on a philosophical and theological ground. And when religion involves nature, then it becomes real. And that thought is something that many find disturbing. But what sets Christianity apart from other religions is that it is not just a set of codes of ethics, but it really touches upon every field of human experience. To me, this is what makes Christianity an interesting worldview. It gives me reasons for trusting it as a guide on then other things like spiritual matters. So today I will talk about geology, but I will only address one proposition within the Judeo-Christian worldview that relates to geology and has been much debated, and that is the concept of catastrophism. The concept of catastrophism was popular prior to the 18th century and was highly influenced by scriptures. Scripture set the stage for a view of the past that included rapid catastrophic processes with a global impact and also mass extinction. Life was destroyed. And then there is the concept of geological time. And this is very much debated, even among Christians. But Christians that do not base their models in naturalism are free to explore other alternatives, even those that consider other time frames, because theoretically, God is not dependent on time and could have created the world whenever he saw fit. But as I say, all this is very complicated. And even biblically, if you take these verses to be literal, then Genesis mentions actually 3 stages of the earth. One, when the earth was without form and void, which we really don't know what that means geologically speaking. Another when God is shaping earth for life, creating the continents and moving them around during the creation week. I mean, these are all, you could say, geological events. And then the third is the Genesis flood, or Noah's flood. And Christians debate about the meaning of these stages and where they are found within the geological record. So today I will not defend any particular model within Christianity, explaining these observations in geology, neither a specific timeline, because the data that I have does not really allow me to do that. But I will focus on the concept of catastrophism. Okay, so that said, let's dig into the topic. Eyjafjallajökull. You all recall in 2010 when the Icelandic volcano Eyjafjallajökull erupted. Many people had difficulties saying the word Eyjafjallajökull for some reason. Maybe Icelandic words are, a bit difficult. But this word is actually a compound word. There are three words. Eyja means island, and it's a reference to the islands, a few islands south of the volcano. Fjall means mountain, and jökull, a glacier. So the mountain with the glacier by the islands. It was an impressive volcanic eruption that lasted about 2 months, with a small eruption preceding the summit eruption. And the explosive interaction of the lava and the ice within the glacier on the summit generated fine ash that could be carried long distances. And that's why it caused the disruption of the air traffic. We had this little joke going on during the economic crisis in 2010, that Iceland would only pay its debt with ash and not cash. I myself worked on Eyjafjallajökull in my graduate studies and actually told a story similar to what happened in 2010. So I was thrilled about that experience. The volcanoes can be natural wonders to watch, as you saw from those photographs of the lava falls. But they generally impose a threat, a danger to the local communities, and thus understanding how volcanoes operate is important for hazard assessment. Now, let's just proceed and look at some terms we will be using throughout the talk. Lava is molten rock. If you heat up volcanic rock up to 800 and between 800 and 1,200 degrees Celsius, depending on the type of rock, the rock will melt and flow, even though it's 100,000 times more viscous than water. The word magma is the subsurface equivalent of lava. So magma is the subsurface equivalent of lava. And because magma is less dense than the surrounding rock, it will rise through the crust. Just like pressing a ball in water, as you release it, it would shoot up. Now, there are different types of lava, and they are classified most often after silica content. You see here, silicon dioxide. Mafic lavas or basaltic lavas make more than 90% of all volcanics on Earth, and they have around 50% silica and are less viscous and more fluid and erupt more passively, while felsic or silicic lava, the dacites and rhyolites, they have over 60% silica and are more viscous and erupt more explosively. Volcanoes form at plate boundaries. The crust is broken into plates, like an egg. If you break it, you'll see little plates. And where there is extension or collision, like for example here would be an extension, or collision, like here, subduction, that we find the volcanic activity and earthquake activity on Earth. But volcanoes can also be found at strange places like Hawaii and Reunion Island. And these have been interpreted as being related to heat anomalies in the mantle or narrow stems of welling magma, more commonly known as mantle plumes. To understand past volcanic activity, we need to first understand present activity. I want to give you a few examples of modern volcanic activity. So let's begin with effusive activity or lava outpouring of basaltic composition. And we'll look at an eruption or an event. It was quite long, 35 years, in the volcano Pu'o. You'll have all heard of Hawaii. Hawaii is a volcanic island in the middle of the Pacific Ocean. The eruption of Pu'o began in 1983 and ended in 2018. It lasted about 35 years. It was an unusual long eruption. It is divided into several episodes that were generally small, producing relatively thin flows. And the average effusion rate, which is the volume of lava per unit time extruded from the fissure, was less than 10 cubic meters per second in general. There were some episodes that were larger, up to 100 cubic meters per second or something like that. The total cumulative volume was about 4.4 cubic kilometers of lava during this time. And one road, for example, was covered with more than 35 meters of lava. And the eruptions covered about 144 square kilometers. 144 square kilometers is a little bit less than half of the area of Peterborough. I hope I Googled that right. But here you can see a small lobe extruding from the lava. And lava flows, they can form a little crust. As you see, they will form a crust as it cools from the surface. And this crust can expand as a little balloon. And then it will grow and the crust will thicken and begin to retain lava. And the lava can inflate. And then when the crust is rigid enough, it will break and it will release another lobe that will spread, expand, inflate, and then release another lobe. So it's a kind of a lobe by lobe emplacement, the walk of the Pahoehoe. And this is, a very, very small kind of eruption. Here you can see, for reference, a river with a very low flow rate, less than the cubic meters per second. Now, the Holotrain eruption in 2014. The Holotrain eruption began in August and terminated in 2015 February. It did not draw much attention because it did not disrupt the air traffic. It was more passive, but it was very large and produced a volume of about 1.4 cubic kilometers. Lava about 1.4 cubic kilometers and covered about 85 square kilometers. 85 square kilometers is about 11,900 soccer fields. So it was about 5 times larger actually than the Eyjafjallajökull eruption in terms of volume. But effusion rates were about average 100 cubic meters per second, peaks of 300 cubic meters per second, lobe thicknesses between 5 and 15. And here you see another view of this event. It was a spectacular eruption. beautiful, in the middle of the highlands of Iceland, and during winter time. It was pretty on a safe location. It lasted about 6 months, and it was very interesting to follow this eruption and monitor it. Now, just to show you a reference, this is a river that has a flow rate about 300 cubic meters per second, similar to the peaks of Holotrain in terms of how much lava was being extruded out of the vents. Now we are getting to larger eruptions, and when we talk about large eruptions, Laki always come in as one of the largest on Earth, actually. Laki eruption took place in 1783 to 84. It lasted about 8 months and was well documented, especially by a local priest that made meticulous descriptions of the events around the eruption. This eruption is considered one of the largest, as I mentioned, and formed a lava field of about 15 cubic kilometers. It was 10 times larger than Holotrain and covered an area of about 600 square kilometers. Average effusion rates were about 1,000 cubic meters per second, with peaks of 8,000 cubic meters per second. Now, here you have a map of Iceland, a geological map of Iceland, and here you see the Laki lava field, and there's actually another one which is of similar size, a little bit larger, called Eldgjá, from the 10th century. So Iceland actually has experienced a few of these very large eruptions in recent times. And here's an example of a river that has an average flow rate of about 1,000 cubic meters per second in China. So you can imagine, if this is lava, how it would look like. Now, effects of Laki eruption. The Laki eruption is said to have released about 120 megatons of sulfur dioxide into the air that reacted with rain and humidity, producing acid rains. It actually produces sulfuric acid and contaminating the surface waters. It also generated widespread hazy conditions that resulted in a cooling effect of about 1 degree in the northern hemisphere, which led to very cold winters and summers with crop failures. These effects combined led to social and economic crises, with famine and diseases indirectly killing about 50% of the grazing animals and about 1/5 of the population of Iceland. The climate impact is said also to have affected Europe and possibly triggered the French Revolution. All right, so let's look at, now here's this map you see with red areas and blue. These are so-called large igneous provinces that produced so-called flood basalts. Now, flood basalts, as the name indicates, are areas that literally flooded. No, these are actually, yes, areas that were literally flooded by lava flows, hence the term flood basalts. If you look at the geological column, they're very common in every geological era. And here, for example, you see conventional geological column down to the Precambrian, while the Phanerozoic and the Cambrian is actually right here, where there's the explosion of life. Cambrian explosion is just around about here. This is the Phanerozoic. So there are plenty of large igneous provinces right here, and these, of course, are the best preserved There's kind of these provinces here in the Precambrian are not as well preserved and not well exposed. But there are plenty of them all throughout the geological record. So yeah, just as I mentioned, so a flood basalt is a very extensive lava flow of basaltic composition that has issued from a fissure, often to be found as part of a series of such flows, one on top of another, forming a plateau. Here is an example of a fissure eruption in Iceland. This one took place in 1984. It was part of a series of eruptions, which were called the Krapla fires. And they were not very big, but they were quite short-lived. I think the one that lasted longest was about 14 days or something like that. But these are fairly long fissures and with several segments erupting lava flows. When we look at the volcanism, we study the volcanism in large igneous provinces. We find out that these lava flows, they covered areas over 10,000 square kilometers. And individual flows reach volumes of over 1,000 cubic kilometers. Recall, Laki was about 15 cubic kilometers. Now, effusion rates have been calculated from 10,000 to 10 million cubic meters per second. Flows in these provinces have average thicknesses between 20 and 30 meters, but some of them reach over 100 meters in thickness. And there are a few examples that we'll be looking at. But here in this image, you see Iceland. There's a scale here, 100 kilometers. Here's Laki. In Iceland, actually, we do have flood basalt areas as well, both here in the east, in the north, and in the west, the older parts of Iceland. And these actually formed flow fields that covered about 1,000 square kilometers. But if you go to the US, we have the Columbia River Basalt, and this is one single flow field, or even one single flow. And it's just gigantic, covered 76,000, you see here, 76,000 square kilometers. This Frenchman spring member, and then Rosa member, about 40,000. So we are talking about extremely large events. And for comparison, if you look at the average flow rate of Amazon, it has about 200,000 cubic meters per second. So some of these flood basalts, they had effusion rates or flow rates in this range, or much larger, up to 1 million more. So you can imagine, vast, widespread areas being covered by lava flows, inundated, flooded, in a relatively short period of time. Here are a few large igneous provinces. We have the Paraná, Etadenca province. The largest part of it is in Brazil, and towards here south Uruguay. And then there's a little part of it here in Africa, which actually just points out that these continents were together at some point. But the Paraná Etadenca covers an area of, with Etadenca, 1.5 million square kilometers, and has a volume of 2.3 million cubic kilometers. The Siberian traps erupted in the conventional time frame in the Permian has about 7 million, covered about 7 million square kilometers, and has a volume of about 4 million cubic kilometers. And there's the Deccan traps, that erupted towards the end of the Cretaceous, and geologists tie this event to the extinction of the dinosaurs and things like that. But the Deccan Triad covered an area of over 500,000 square kilometers and has a volume of about 1 million cubic kilometers. Now, one of the best studied igneous provinces is the Columbia River Basalt Group in the US, in Oregon, and Washington. Covers parts of Oregon and Washington and Idaho. And individual flows in these group, they reach volumes of up to 4,000 cubic kilometers. So, and they flowed lengths over 400 kilometers. So, and the fissures that produced them were over 100 kilometers long. So these are very large events. Now, if we go to the Precambrian, we also find some extremely large igneous provinces, but they are not well preserved, as I mentioned. Here, for example, in Canada, we find evidence of intrusions. These are dikes. It's called a dyke swarm. And most likely, many of these erupted at the surface in long fissures. But you see here the scale, 500 kilometers. So these are thousands of kilometers long dikes and possibly fissures that fed probably very large areas. And this is in the Precambrian. And if you go to Africa, there's another case, you see 100 kilometers here. These are also dikes, intrusions that probably fed very large eruptions. So we are talking about very large events here. Now, if we look at the morphology of the lava flows, how they differentiate from modern eruptions, then all the way to flood basalts. If we give just as an example here, this is just these numbers here are just for reference, but they do work. A lava flow with very low effusion rates, average effusion rates, about 1 cubic meters per second, will form a lava flow and flow field with relatively small lobes and flows of different dimensions, sizes, and shapes. They would possibly reach, after inflating, maybe 2 meters, 1 to 2 meters. But this is how a flow, very low effusion rates would look like. Now, if you scale the eruption up a little bit and go up to 100 cubic meters per second, well, then the lobes start to thicken and are larger, but they are still, you have quite a range of thicknesses and dimensions in the flow field. So here the flows are inflating to 5 to 10 meters maybe. Now, if you scale the eruption up to 1,000 cubic meters per second, then the lobes start growing even larger, and average thicknesses maybe 10 to 20. But if you go over 10,000 cubic meters per second, then the lobes, the sheets, they turn into large tabular flows with relatively flat surfaces, and it becomes can extend several kilometers as just single sheets. And so in the field, if you would look at a mountain and would see these different types of morphologies, then we have what we call simple flows or tabular flows. These are these very extensive sheets that form that very high effusion rate. And then we have what we call compound flows. These are flows that form that lower effusion rate. Of course, both type of eruptions, those very large and smaller, they do form, in a sense, compound flows because they do form several lobes, but the lobes and the flow fields just scale up with higher effusion rates. And as effusion rates become very large, then you get this impression here of flooding. So it's just like actually if you open the tap at very low flow rates, then the water will flow, controlled by the microtopography and form little streams. So in lava terms, these little streams will form, little lobes and flows. But if you open the tap and then you start getting larger sheets of water until the entire area is flooded. And that's kind of an analogy explaining these different architectures and morphologies we see in these volcanic areas. Walker was a British geologist that worked in Iceland a lot, but also in several other places. He studied flood basalts a lot. And he says flood basalt points, such as constitute the Columbia River Plateau, the tertiary lavas of Iceland and the Faroes, and the Deccan Fremps of India, include both simple and compound lavas in their makeup. So in large igneous provinces, you do find these two types of architectures. And so here is a view of an image of a compound flow of a relatively small eruption. Could have been long-lived. This is actually part of a lava shield. And you see all the lobes here, different dimensions and sizes. So, and relatively small dimensions. So it's relatively low effusion rate. While when you go to these flood basalt provinces, large igneous provinces, like this is part of the North Atlantic igneous provinces, this is in the Faroes, then you start getting these massive flows, very extensive, and sequence of them. While on the top here, you see a section of compound flows. You see, you can't really define their dimensions. So these are evidence of these simple flows or tabular flows, give evidence of massive outpourings of lava. If you go to the Columbia River basalts, then you see these flows are very thick. Some reach up to 100 meters thick. These are probably 20 to 30 meters thick that I have here in these photographs. When we go to the Paraná, the Brazilian side has about an area about 1 million square kilometers. Then we see these massive flows. You see here a track for scale. This is one flow, and this is another one. In about 20 meters, this is about 40, and they're very widespread like this. You travel through these provinces, and the flows are just gigantic. You go into quarries like this, and these are just very often just single flows, tens of meters thick, and very widespread. In the North Atlantic igneous province, which actually is related to the Icelandic mantle plume, which is still active actually, and probably is probably the one that is erupting these very large Holocene eruptions in Iceland, like Laki and Helgja, Þjórsá and others. It began here actually in Greenland and in Britain actually. The giant causeway is actually part of this North Atlantic igneous province. And when you look at the lava flows, for example, in Greenland, there are these extensive sheets with plain parallel surfaces or very flat surfaces covering very large areas. And as I showed you here in the Faroes, on the other side, the same. Very extensive flows. And then we go to Iceland, actually. This is part of the Miocene stratigraphy in Iceland, the older parts of Iceland. And we still find these very extensive flood basalts, and I have actually studied these in detail and published papers on them. But this is a section a few kilometers long, and it's just single sheets all the way through. And I have traced them over 60 kilometers, this sequence here, and they all look the same, just single sheets. So, yeah, volcanic activity was pretty violent and massive in these areas. And these are other examples from Iceland, a little bit thinner flows, but still very simple, flat surfaces. And then you see one and one ending here. One lobe ends here, but it's covered by another one. And here you have a very interesting sequence of flows that are so uniform. And I actually tend to talk about these as uniformity of catastrophism, because you just have these repeated flows with the very same properties, same morphology, one after another one. But in standard conventional time, this sequence, for example, is dated about 1 million years. So they are, in the conventional time frame, tens of thousands of years in between each lava flow. So each catastrophe is separated by tens of thousands of years, but still it somehow can generate the exact same kind of type of lava throughout its volcanic history, which is quite intriguing, I would say. And I actually have issues with that kind of thinking. But yeah, this is how it is. Flood basalts. Now, if we look at explosive activity, here's an example. You're all familiar with Mount St. Helens. And you see here how it is small compared to these other eruptions here from the past. Yellowstone, and Toba, and Tambora, Krakatoa. These are very large eruptions in the past, explosive eruptions, up to volumes here 2,500 cubic kilometers. While Mount St. Helens was less than a cubic kilometer. Eyjafjallajökull was about 0.25. And if you go to the Mesozoic, when to the Paraná, large igneous province, there you find igneous rise at about 8,000 cubic kilometers. So on a volcanic explosivity index, just return here, which is based upon the volume of tephra produced during an eruption. You see here magnitudes, and this is a logarithmic scale, so 10 times larger each magnitude. And Eyjafjallajökull was around here 4 on this volcanic explosivity index. Mount St. Helens was here also about 4 or 5. But then there are these past eruptions here that reach, index of 6, 7, up to 8, and cause massive destruction. Okay, so what causes flood basalt volcanism? There are in general 3 explanations that have been given. One is shallow mantle processes. Some people think that these mantle anomalies, they are only related to ripping apart of the continents during plate tectonics and subduction zones. While there are others that think that these are more deep processes. They're related actually to subduction of crusts that sink down through the mantle all the way to the core mantle boundary. And as they reach the core mantle boundary, they produce melts that rise through these narrow streams in these what we call metal plumes, and then reach the surface. That's another explanation. So both actually related to plate tectonics. The one let's only look at kind of shallow processes, while the other one considers more deeper processes. Then we have meteorite impacts that are also candidates for explaining some of these. And we have evidence of probably around 190 impact craters on Earth. Not all certain, of course, but we do have evidence of meteorite impacts. And they could certainly have generated some of these volcanic anomalies. But we could also, it is possible that what triggers these anomalies would be a combination of all these three. But we do have evidence of plates at subduction zones, kind of sinking all the way down to the core mantle boundary. This is an image done with seismic tomography, when geologists use seismic waves to kind of scan the interior of the Earth. Then they find these different properties of within the mantle that give different flexions, refractions, and then they can map structures in it. And here is apparently a structure that has sank from the upper parts area here of the crustal parts to the core mantle boundary, and it's called the Farallon plate. And this is a little bit more complex to figure, but it just shows actually how these subduction zones provide with crustal slab. These are oceanic crust that sink all the way down to the core mantle boundary. And there are actually two zones here called low seismic zones that some people do not know exactly what they are, but they have different compositions and properties, and some think that these are actually crustal cemeteries where they accumulate here, and then these mantle plumes, they emerge or rise from the boundary or from the margins of these zones. And there are two zones that they have mapped here at the boundary between the core and the mantle. So and actually there are some interesting theories around this. Some are actually now correlating the frequency of mantle or large igneous provinces, or activity within these large igneous provinces, with the frequency of magnetic reversals. So the core actually works as a dynamo. It is made of iron and nickel, and the outer core is actually liquid. And if there are movements within it, then it can actually generate movement within the magnetic field, which protects the Earth actually against cosmic rays. It's a pretty cool thing that we have this magnetic field. But if there are movements within the liquid core, this magnetic field can wobble and even go through reversals. And there's a theory actually that says that when there's lots of plume activity, lots of heat flow from the core to the surface, then you have higher frequencies of magnetic reversals. So this is an interesting model that seems to unify several observations that we make on Earth, like the magnetic polarities, their distribution in the oceans, and how they form and all. And so they seem to be related to these deeper processes. Okay, the more we learn about volcanism, the more we realize how often many systems are affected by it. I have found out that this is very important in my mapping to be aware of this. For example, an eruption can be followed by earthquakes. Earthquakes can generate landslides, slumps, density currents in water, turbidites. A graben system can form with faults, cracks, and fissures. The system can then subside several meters in one event. Large areas can be covered by ash. And this ash actually is a good fertilizer, but it can also just bury and kill the soils. But large areas can be covered by lava, changing the local topography and destroying the flora and fauna. Explosive eruptions can erode the vicinity of the crater. Landslides and lava flows can dam rivers. The blast of the explosions can wipe entire forests and bury them, as seen in the Mount St. Helens eruption. The intrusions associated with the eruptions can heat up the local groundwaters and form hydrothermal systems around it, altering the rocks below the volcano. Alteration of rocks can speed up the precipitation of minerals, carbonates, in voids, in holes, and vesicles in the rocks. The volcanic vent can expel a huge amount of gases that can have an effect on climate, as happened during the Laki eruption. So sulfur dioxide and aerosol will sustain hazy and cloudy conditions that will block the sunlight, causing a cooling effect until it is washed down with the rain, while greenhouse gases, like carbon dioxide, will persist longer and cause a warming effect. Even ash deposited on the seas can generate algae blooms that will deposit at the sink and deposit at the bottom. This was actually seen in the Eyjafjallajökull eruption. And volcanic eruptions in watery environments can generate massive amounts of sediment. They can also mobilize water bodies in large floods that will carve canyons in hours. Volcanoes on the glaciers in Iceland have these effects, actually. They melt parts of the glaciers around the vents, and this meltwater escapes in huge floods that we call jökulhlaups. And many of our canyons have been covered by such floods. They also deposit several meters of sediments on the sand plains. Here's an example of one of these events in the Gjálp eruption in '96, and produced a large flood. These are actually the sand plains right here, and very sediment-rich water. And these and it destroyed the bridge, actually an iron bridge that was located here. And flooding events like this in Iceland, some of them reached actually 300,000 cubic meters per second flow rates, and they carved canyons like this. Most of our canyons in Iceland actually are related to these catastrophic outburst floods, and they have extreme power. They can, carry bridges like this, iron bridges, and huge boulders, long distances. And this is the sediment deposited in this event and other events. And this is actually the Vatnajökull glacier, which provided the meltwater in this eruption. But what are the effects of large igneous provinces and flood basalt volcanism? Now, they must have been colossal. Not much has been done to look at these other systems around flood basalt volcanism, like sedimentation, erosion, and so forth. But as you see, here is this figure. Areas of thousands of kilometers affected. The landscape is totally transformed and life completely eradicated. Now, intrusions can interact with coal seams and methane deposits, with organic matter in the sediments, releasing a huge amount of greenhouse gases. And the volcanoes release massive amounts of water vapor, carbon dioxide, and sulfur dioxide, with devastating climatic effects. And actually, the effects on climate are being explored quite extensively nowadays in relation to these large igneous provinces. You see from the schematic figure here that people are beginning to tie flood basalt volcanism with climate change. anoxic oceans, ocean acidification, which eventually lead to mass extinctions. Now, many of you are curious about how all this relates to a unifying model of origins. And the geologist inside you is kind of jumping out. If that is the case, then I think I have accomplished my goal with this lecture. But let's put this into a historical perspective. In the 17th and 18th centuries, geologists were mostly catastrophists. In other words, they believed the biblical narrative of creation and Noah's flood within a much shorter timeline. Georges Cuvier, a French naturalist and a Christian, the father of modern paleontology, wrote, "All of these facts, consistent among themselves and not opposed by any report, seem to me to prove the existence of a world previous to ours, destroyed by some kind of catastrophe." Here he links the fossil record to a mass extinction caused by a catastrophe. He first actually was a proponent of a single catastrophe, which he related to Noah's flood. But later he changed his mind to multiple catastrophes, and the flood of Noah was somewhere at the top. And this view actually of multiple catastrophes became popular among many naturalists. But after the death of Cuvier and with the Enlightenment, scholars began to doubt the validity of scriptures. And a new science, championed by geologists like James Hutton and later Charles Lyell, which was a lawyer, turned geological thinking towards deep time and slow and gradual processes. Their maxim was the present is the key to the past, and catastrophes were almost eradicated from geology. Later, with the discovery of radiometric clocks and their application in dating rocks, yielding millions of years, uniformitarianism was established and would become embedded in geology. But in the middle of the 20th century, geologists began to again postulate catastrophes of large magnitudes. A prominent one was J. Harlan Brent, an American geologist that suggested several cataclysmic flooding events over this channel of scablands of Oregon and Washington. And he suggested this in order to explain some peculiar formations in that area. He and another geologist proposed these floods had formed from the repeated drainage of large periglacial lakes. This is the ice sheet during the Ice Age. Nevertheless, he encountered fierce opposition by uniformitarians that tried to explain the scablands with slow and gradual processes. Eventually, his ideas were recognized by the geological community, and he was awarded an honorary medal from the Geological Society of America. In recent years, catastrophism is slowly entering the back door. Professor Aya Derek, that was the head of the geology department at the University of Swansea in Wales, says in an article in the New Scientist, "There is no doubt that catastrophism, which was still a laughing matter not very long ago, has returned to geological theory. More and more books and papers are being written about the rare event and sudden, often violent happenings. This is true in every field of geology, from extraterrestrial impacts to continental collision and from stone deposits to episodic evolution." He also says, "The hurricane, the flood, or the tsunami may do more in an hour or a day than the ordinary processes of nature have achieved in 1,000 years. Given all the millennia we have to play with within the stratigraphical record, we can expect our periodic catastrophes to do all the work we want of them." And he also says, in other words, the history of any one part of the earth, like the life of a soldier, consists of long periods of boredom and short periods of terror. And this is more or less what summarizes the Neocatastrophist view that actually is predominant today, that they do accommodate large large catastrophic events like these volcanic eruptions, meteorite impacts, massive extinctions, and other events, but within conventional deep time chronology. Now, another professor, Robert Dott, said, "What do I mean by episodic sedimentation?" Episodic was chosen carefully over other possible terms. And listen, he said, catastrophic has become popular recently because of its dramatic effects, but it should be purged from our vocabulary because it feeds the Neocatastrophism creation cause. I hope I have convinced you that the sedimentary record is largely a record of episodic events. In other words, catastrophic, a word that he didn't want to use. Now, episodic events rather than being uniformly continuous. My message is that episodicity is a rule, not the exception. All right. So where is geology heading? Now, for me, personally, I'm more interested in that question than where it has been. And certainly, there have been there are arguments for these different views and different concepts that have dominated geological thinking throughout these last centuries. But where is geology heading? And from these quotes and from the observations in this lecture, we can conclude that catastrophism is back, and it's not just back, it's on steroids. Well, catastrophes in the geological record, even of global impact, are the rule rather than the exception. And that is very interesting because it does affect our understanding of time. And why? They can form widespread deposits in a short time frame that otherwise would take a long time. So yes, it does. By studying catastrophes can affect our understanding of time. And but of course they need to be carefully mapped and studied. But I want to make a few additional remarks. Understanding our catastrophic past is important for mitigating present natural disasters. Understanding our catastrophic past can also help us mitigate anthropogenic hazards. Now, we are, for example, dealing with what we call a climate crisis, and understanding these large catastrophic events can maybe help give us hints or help us mitigate the hazards that we actually are causing as humans by burning fossil fuels and polluting the environment. Well, another significant thing that I want to point out, and as you saw from these quotes that I read, that it seems like a catastrophic past or catastrophic notion is deeply linked to a narrative which we find in scriptures. So these catastrophic past will undoubtedly lead us to the narrative of the old good book, which somehow wanted to inform us about it, and maybe to tell us that the future is brighter and things are going to be all right. Now, if you are uniformitarianist, or and you think that things are come in cycle, that large-scale events like this will just be repeated in the future, the scriptures tell us a different story. It says actually the future is brighter. Things are going to be all right. Well, I want to thank you for watching. I hope this lecture was informative. It was a bit new, the format for me, just to speak to a screen. But questions are welcome through the channel, and I just wish you all the best.
Thank you so much, Birgir, for your presentation. And as he said, please send your questions in on Saturday at 6 p.m. We will be taking a question and answer program, and our speakers are looking forward to being grilled. Tomorrow, Dr. Isabel Moraes is going to be discussing with us Mankind, the Masterpiece of God's Creation. Mankind, the Masterpiece of God's Creation. We are looking forward to seeing you then. But as a general reminder, please don't forget to send your questions to godandscience.co.uk. And if you know any of us on the panel, shout out and we will take questions also on your behalf. Look forward to seeing you tomorrow. Please take care. Bye-bye.